Hi, this video is part of a series in which I learn about programming a retro video game on the Commodore 64 in assembly. The code I'm using is from the game Supernatural, written by Georg Rottensteiner. You may also know the game as Guns and Ghosts. This is not a tutorial, just me learning game programming. Enjoy the video. Coders, hello. Welcome to step 33, where we are going to make the zombies and the mummies a little bit more interesting. We're going to be looking at the code that is required to make them do more stuff. So the idea for the mummies is to have an attack mode. So when it sees the player, it's going to rush towards him. So we have to detect whether it's on the same Y coordinate and then on the same X coordinate, actually looking at the player. So if it is going right, we have to make sure that its X coordinate is smaller than the player's X coordinate, and the opposite for the opposite side. So that's going to be something. Also, the mummy, the zombies, they just walk left and right now without falling off a ledge. We're going to make it so that they can fall and that they can jump. Now, up until now, it's only been the player sprite that has been able to jump and fall. So we're going to generalize those tables. So the jump position will be a jump position for each and every sprite. So we'll have a look at what it looks like, what it does, and then we'll go over the code. So let's go. So here's the game. I think I have the controller set up. Yeah. So this field is nothing new. It's just it's got the different behaving zombies on it, and the background is a little bit different, but that's just because we're starting at a different level in this one. You can already see that the zombies are jumping at random moments, and they are falling off ledges now. So you can also see that they have an actual walking and jumping animation. So there's new sprites there. Poof, shot them in the back. There is one mummy at the top, which I'm going to demonstrate its behavior. So it's not attacking me now, but it is now. And if it sees me and it's on the same level, it's going to attack me. See, and it also has a walking animation now. So that's two things that we have to do. We have to change the enemy behavior. And we also have to add the code for the actual animations. Well, you can see what the animations look like, but we'll have a look at the. Hey, did you see that? For some reason, the mummy actually see it goes into attack mode, probably because that is the location where I was when I died. It's still attacking the location. See that? That's fun. Yeah. Let's have a look at the little sprite thing. Where's my C drive gone? Ooh, there we go. Supernatural, and we'll go to the spriter, and we'll open. That's nice. We'll open the right file. You can see what how I organize my disk. Is that great sprite project? There we go. Here's the overview. So you can see that there's the Sprite 34. This is the only thing that we had the last time, and now we have these, and we have the walking and the attacking mode. So as always, we look at the data first. As you can see, or as I probably should say, as you can't see now, there used to be player jump position here, but that's been changed. Because now, if we go a little lower, it's a bit hidden, but there is now a sprite jump position table, which for some daft reason I cannot select anymore. Oh, okay. I installed a new version of the development environment, but that doesn't allow me to select. Oh, it doesn't change the background color of the text, so you'll have to. Yep. There's a sprite jump position table. There's a fall position table. So this is now basically just a table indexed by sprite number. So the first character is always going to be the player, right? And there's a fall position, and it says whether the sprite is falling. But we had that, and that we had the direction, and new is a direction Y. We'll get into that because the bat sprite direction used to be only left and right, but we're going to have enemies which move in all four directions. So we need a second direction table, which is direction Y, basically up and down, and this is left and right. So this should be called direction X maybe, or horizontal and vertical, or whatever, but this is what we have to deal with now. There's also something we already had sprite state, and now we have sprite annoyed. Now technically I would say that that is a separate state, but now we have a table which we can use to say that a sprite is annoyed. Perhaps it's a temporary table, I don't know. We only use it in one location. You'll see as the code develops that some ideas are added and they're a bit silly and they get removed later on. But right now we have a separate state which has its own table, and we can annoy a sprite and base its behavior on that. If we go down a little bit further, we'll see that the bat left and right has become bat diagonal. So the bat that was moving left and right has now become a diagonal bat, and the rest are still the same. So there is something else, which is the enemy start direction. For each sprite type, enemy type, basically, we can now set a byte that will tell the game something about its starting direction. Will it start going left? Will it start going right? Or will it be random? Now, the way this is set up is that there's 8 bytes per sprite type, and the first 2 bits indicate its starting direction in the horizontal way, and bits 2 and 3 tell us something about up and down. Now, if we put a 0 value in any of those sets, we get a right movement for X and an up for Y. 1 is left, or it's even more confusing when I say it wrong. So in the horizontal direction, 0 is right, 1 is left, and 2 is random. In the Y direction, it's up, down, and random. So as you can see, the player direction is right. Enemy type 1, which I don't know by heart, of course, but enemy type Oh, 0 is nothing. Type 1 is player, right? So it's a waste of a byte. And then come the so 0, 1, 2, and 3. The bat diagonal and the bat up and down. So the bat diagonal has 2 and 2. 1, 0 is 2, meaning random in the X and the Y directions. The rest are all random in the right direction, and they have no up and down. So these values are all used excuse me, are all used when the game is started, just to set the starting directions. Yeah. And that's it for the well, the levels have changed to reflect the new enemy names, but that's nothing to lose any sleep over. So let's go to the top of the code, which I've just done, and we'll look at some of the changes. You can see that I now have this line 106 reflects the new sprite shape for the mummy going left and mummy left 2. We just had mummy right 1 and mummy right 2. The mummies used to change shape, but only in the right direction. So now they have a sprite for the left and the right direction, and also one attack form for left and for right. So this is just basically adding the new sprite shapes, and we have the new sprite zombie jump shapes also for left and right. So the mummy has an attack shape and the zombie has a jump shape. So we've added those. At least the game knows of their existence and can set them now. As you will see, scrolling the wrong window, 158 here. This used to be called bat left and right. It's now diagonal. So there's a lot of find and replaces just to change the name of the sprite. You can also see here. Where was that? Sorry, go up. Just scrolling down to where the game sort of begins, 429. You can see that we start at level number 3 now. It used to be 7, but we're doing that to demonstrate the new behaviors. The first location where we actually see something interesting happening, apart from the fact that everywhere that we use the player jump position is now changed to sprite jump position. Maybe we can look at one of them, 1701, which is line 1701. It'll become apparent. This used to say this doesn't really matter which routine this is in, but now we have to use the sprite jump position because this used to be player jump position, which was only 1 byte. Now it's a table. We can suffice by changing the name of the table because we're not indexing it, which automatically implies that we're using the first element in that array. Comes down to the same thing, of course, but that's what we have to do when we change that jump position byte into access into a table. So, and there's a couple of positions where that is done. Some of the changes, I'll show you something that is it's just funny. Doesn't mean anything. At the end of this routine, fire shot. So the player fires a shot, and then at some point you want to jump to shot done. Now this was at the end of the routine, and it's been moved, I think, because when you do a relative jump, like in a branch equals 0, or when you do a branch, you can only jump 256. No, I think 120 bytes forward or backwards. So at some point, that's going to be too far, and you're going to get errors, which are very difficult to catch, by the way, if you don't have any debugging. So I'm thinking this happened. So Georg moved this code closer to where the call was done. But it's just an RTS. And the funny thing is he's moved it to a place where there already was an RTS. So now it looks like this. So if you debugged this code, if you disassembled this code, you would find a location where there are 2 RTSs in the code right after each other, which looks a bit silly, but I do get it, because when you're programming, what if you want something else to happen when the shot is done, like play a sound maybe? You can add it here without having to think. If you put shot done here and use this RTS, you may get yourself. So you may get yourself into trouble. So this looks a bit weird, but no one ever said that this was perfect code. It's just it just looks funny. Now, here's the thing. Check enemy. Right? So when the player fired a shot, at some point you're gonna have to check whether you hit an enemy, yes or no. Now we've added something here. I've added this comment myself. Remember that each sprite has a state. Apparently, it's you can set an enemy to be invulnerable, perhaps for a short time, perhaps for a longer time. But if it has a certain state, which is above 128, the enemy cannot be harmed. So basically, you just load the sprite state, compare it to 128. If it's above that, then or equal to, then you check the next enemy. Check next enemy is basically just going back up. Oh. No, check next enemy. Where is that? Maybe I can jump to it. Or go to declaration. Oh, yeah. Yeah, so you go to the next enemy. Shot continue. So it's easy to implement that, because all you have to do now is to find the places in the code where if an enemy is hit, it has a hit behavior routine. You can set it to this value, and then you have to make sure to move it out of that value at a different kind of event. But this perhaps when the mummy is attacking, it's invulnerable, or most likely when the zombie is hiding, when it's collapsing, maybe that's the moment that it's invulnerable. So we have this in place now to make sure that if the player shoots, some enemies cannot be hit at certain times. Then we go to, well, the bat behaves diagonally. Let's go to the bat behavior. Behavior bat diagonal. We're gonna behavior bat diagonal. There we go. This is just all the ordinary code, except that now we have a move Y. So after we've done the animation stuff, we basically do the same that we did for X, but now for the Y position. So this is the whole bit. Normally the function would end after toggle direction, because when the bat is moving in one direction and it's blocked, and it changes direction and it goes like this all the time. Now it has to move in a different direction. So this is where the sprite direction Y table comes from, or comes into play. So we load its current direction. If it's equal, then we move down. Otherwise, we move up. The object move up blocking actually moves the sprite if it can. And if it is blocked, then it will tell the calling routine by setting a value. I think it's the accumulator to 0 or not. And so when it's blocked, it just toggles direction in the Y. So it goes from moving up to moving down. Otherwise, it goes the other way logically. You know, we loaded the current direction. If it's equal to 0, then we're blocked, or we're moving down. So we try to move the bat down. If it's blocked, then we toggle direction. And toggling direction is basically just loading the direction, doing an exclusive OR on it, which always flips the bit. And since the direction is just either a 0 for down and a 1 for up, it just changes like that. So we've done the X movement and then we've done the Y movement, so we get a diagonally moving bat. And that's the power of having a routine that is well written. We can just call it and not worry about anything. So it makes it very, very easy and very powerful. So that's done. Now we come to the behavior of the mummy. So we've done the bat. I don't think I mentioned the bat at the beginning, or did I? Well, it's gone from horizontal to diagonal. We've seen that now. The mummy. So that's the first thing that we look at here is whether we're ready to attack the player. So we check the sprite, the character Y position. So we want to make sure that the player and the mummy are on the same height on the screen. If the player is lower, then obviously the mummy is never going to see the player. So we compare them. Sorry, we load the sprite character position of the sprite that we're looking at. We compare it to the sprite character position of the player, which is the first element of that table. If there is a difference, so basically this does a subtraction and the end result is not equal, then the player is not in sight. No player in sight means that we just go to what used to be the regular routine. So we go back up to this routine to look at the case of what happens when the player is in sight. Then we have to start looking at whether or not they are facing each other. So we load the enemy's sprite direction, its horizontal direction, left and right. If it equals 0, then we're looking right. Otherwise, we're looking left. Then we compare character positions of the enemy and the player. If the result is plus, then I'm looking at the player. Otherwise, there's not a player in sight. If we're looking right, it's just the other way around. We compare the two, branch minus, looking at player, otherwise no player in sight. So that's easy enough. We've looked at the Y position, we've looked at the X position and whether they're facing each other. Yes, we're looking at the player, so what happens now? We first do the animation, so we set we take the first sprite mummy attack pattern, the shape. We add its direction, adding 0 for moving right, adding 1 for looking left, and then we store that shape in the sprite pointer base. At this moment, the actual the VIC chip starts drawing the correct shape for this sprite. Then we load the sprite's direction, and if it was 0, then we're going to attack right. We have to move in a certain direction. Otherwise, we have to attack left. What it does, it just calls object move left blocking twice in a row. So in one frame, it'll move 2 positions. This is why the mummy was moving extra fast. This is how you get. You could just add another call and it would go faster. You could remove a call, it would go into attack position, but it would move slowly. And remember that the regular direction takes into account waiting a couple of frames before the actual moves, and otherwise the sprites would just move much too quickly. And then, of course, even when we're attacking, we can toggle the direction as soon as the sprite hits a wall, and then basically we're done. When we were attacking right is the same shape of code. It just calls object move right blocking. Toggle direction RTS. When there's no player in sight, basically nothing happens, but we still want to change change the sprite, because now we have more than one sprite shapes for the mummy. But we've seen how that works before. We increase the sprite move position, which is just a number which increases to tell us which shape we can get. We do make sure that it doesn't go above 3 bits here. This is just a standard bit mask. If you AND something with a number, then everything that is 0 is sure to be 0, because you're doing an AND. And all the bits that we're setting to 1 will have the value of the value that we're ANDing. So we store that back into the sprite move position, so that we know that we don't go overboard, because we're selecting sprite shapes and we have to make sure that the sprite move position value is correct. We compare it to 2 can move R2 customer directions can move. Oh, okay, so right, yeah, okay, so we set it to R2, add the direction and write it to the base. Otherwise we take the R1 position. So it's basically toggling between two values here. And then we move right. Is there anything else? No. Object walk left. Object walk left and object move left is an object that walks on the ground and can fall off. An object that moves left and right basically doesn't fall. It sort of floats. So the rest of the code is the same, except for toggle direction, because now we actually have more than one shape. So when the sprite toggles direction, we have to reset the shape. Okay, so that's that. So we basically just added the attack code and the animation for the sprite, which isn't which is what we wanted to do. Now we have to look at the zombie, because we want to make the zombie fall and jump. So let's go to behavior zombie. I added these question marks because the zombie can fall off, but the comments still said don't fall off. But of course, It's exactly what we want. We start by checking whether or not the zombie is jumping. Now that may sound like a strange thing when you add a new behavior, but when you call this routine, and because this routine is called once each frame, so the zombie may be jumping as we speak. So basically we check the sprite jump position. So X is always the sprite number that we're looking at, and we're checking whether or not it is jumping. If it is jumping, then we go to this code, which is basically wait for the next wait for 3 more frames before we can actually do something. If it is not jumping, then we try to move the object down, which is basically doing the falling motion. If you can remember, when we started adding the physics for the player object, is that we didn't actually, the very first version of the code had the behavior that if we pull the joystick down, the player would go down, which is a bit odd in a platforming game. So then we added calling the routine to go, to pull the player down and just not read the joystick for down anymore, which is basically creating gravity. Now we're doing exactly the same here for the zombie. So if it is not jumping, and I'm just wondering what happens, because basically if it is jumping, we're waiting. Movement update. Okay, we'll look at the movement update, because as we jump, we also want it to move down. So if it is not jumping, anyway, if it is not jumping, it is just walking around, and then we want to try and pull it down. If we cannot pull it down, if it's not equal, then we're falling, and then we're doing nothing. Okay, so if we try to pull it down and we can, it is falling. So we've just moved the object down, and then it's not being blocked, so we're ready, right? So we've moved it down, so we're done. We're just falling. If we are blocking, then we get to here, and we basically do the movement update. We don't do it every frame, we do it every 3 frames so that we don't move too fast. So the movement update, I don't think, yeah, there's some change here, because we look at whether or not the object is jumping. If it's not 0, then we have to update the jump. Otherwise, we load the sprite state and we do all the rest of the code. I want to know what happens in the update jump. Update jump. So we increase the jump position. This is shape, right? So we increase the shape. We load its current value. We make sure that we don't go beyond, because we have a jump table, right? So, we have the jump table that says for each frame how many pixels the object moves. So we test whether or not we've had all those positions. If it's not equal, then we continue the jump. Otherwise, we say the jump is done. And basically, we load the jump position. We load the value of the jump table, which is the number of pixels that we have there. Keep jumping. Jump continue. Object move up, blocking, right? So this is the actual jump. Unless we're blocked, so the jump can be blocked as well. Is that new? Is that all new? Yeah, that's all new. Jump blocked, and then this is all the collapsing code. And this is jump. This is where we start the jump, but we want to know, starting the jump is basically putting the player into jump shape, clear, add the direction and the sprite pointer base. But when does it start the jump? Oh, here. Okay, so this is the movement update, right? So suppose we weren't jumping, so we load sprite jump position, which is just 0. So if it's not equal, then we update the jump. Otherwise, we load the state. If it has no special state, then we generate a random number. We compare it to 17, another random number. And then when that equals, then we jump. Otherwise, we do the normal walk. So the normal walk will be this, which was just the same as we already had it. We increase the animation, can move, blah blah blah. We've all seen that. This is quite a complex little routine. Okay, so normal walk, and otherwise we just do the jump. So here's the thing. We check if we're jumping, so then we do the code that we need to do while we're jumping. Then we try to move it down. If it's being blocked and it's falling, nothing special going on. So we're not jumping, we're not falling. Then we end up in the is jumping code, which basically leads to the movement update. And the movement update does all the regular stuff, but we check whether we're jumping so that we can update the jump. We check if we're collapsing because there are other states, which I won't go into, but because we've already talked about that. If there's no special state, then we basically do the normal walk, but we've included this new code where we can decide whether or not we are going to jump. And if we jump, we do this. If we don't jump, we do that. We do the normal walk. And if there is a different state, then we do all the other states. Right. Which included the hidden state. So this writing of the code for the zombie is, I mean, the more complex you want the zombie to be, because we want the zombie to do a lot. We want him to walk around left and right, bump into things and change direction. Then we want him to jump. We want him to collapse and hide. We want him to behave in a certain way when he's hit. So it's quite a few things, but they are all in here and they do make sense. And basically it's just using all the tables that we have and using the routines for moving them. And the jump routine is basically just setting him into jump shape. We increase the sprite jump position so that the next time we enter this routine, we can check that. Are we jumping? Yes, we are jumping. Okay, do the movement update. So we do the movement update, which is also the path we take when we're not jumping. Movement update, where is it? Is here. Again, we check, are we jumping? Yes, we're jumping. So we update the jump. If not, we just walk, or we do any of the other states. And if we're doing nothing, we can still decide to jump. So, but if we do the update jump, then we increase the jump position, we load it, make sure that we're still on, and then we either continue with the jump, or we've done all the jump things and we're done, and we reset the sprite jump position to 0 so that the next time we'll just be walking again. Jump on, we load the sprite jump position, we load the jump table, keep jumping, And this is where we oh wow, keep jumping. So we take the number of pixels that we want to jump, we store that in parameter 5, then we say just move the object up, decrease parameter 5, jump continue. If it's not 0, oh, okay, jump continue. Okay, so this happens all in one frame. So if he jumps, because they jump pretty quick, object move up blocking. See, so this jump table says the number of pixels that the sprite should move during each frame, and that goes from one, from a low value to a high value, because when you jump, or it goes from a high level to a. Let's look at this jump table. Remember 3058, and we go to this, go to declaration. Right, so the first frame, 8 pixels, 8 pixels, 7532, and a couple of ones. So you go like that. 3058. Oh, behavior zombie. Thank you. So this jump table. So we get the number of pixels. If it's not equal to 0, so that's during all of those first phases, we do keep jumping. We store the number of pixels in parameter 5. We do that because the call to this routine will mess up all the registers. Object move up blocking, so we move him up. If the jump is blocked and the jump is blocked, then we're done jumping immediately. Otherwise, we decrease parameter 5, which is the number of pixels that we wanted him to move, and then we move him again. We keep moving him until he's blocked, or until decrease parameter 5. 87654 decrease. Oh, if it's not equal, otherwise, if it's equal, then we're done. The jump is continued, but that all happens within the same frame. Wow, it's a lot of thinking, isn't it? But it's all there. It makes sense. Behavior zombie. Didn't we just do that? Behavior zombie. Yes, we did. Boom. Boom. Generate random number. Yeah. And then we did the whole jump thing and the can move thing. Yeah. Oh, okay. Hit behavior hurt. This is funny. Hit behavior hurt. There used to be nothing here. Hit behavior hurt was nothing. And now we just put a 1 into the sprite annoyed thing, but I don't think that's used anywhere. So if we just go through the code and look for sprite annoyed, I'll move this out of the way. Find next. Okay, it's where it's set to 0. This is the original. Okay, so it's not used yet, but at least we know that we can annoy a sprite, which is also good to know. Always good to know. The clear object, if we go to the build screen, but this is all initialization code where we have the new tables and we have to initialize them to 0. So that's that just makes sense. Yeah, that's something. Use start direction. Okay, yeah. This is something that we may want to look into. Multicolor done. Is that build screen? No, where's multicolor done? Well, 4071. Oh, it's just below here. 4071. There. We have the new start direction table. So we load that value and we compare it to 2 branch not equal set direction X. Otherwise generated. Okay, so if it's 2 So if it's not 2, then we set the direction. Otherwise, we generate a random number. We AND it with 1. And then we store that. Why do we AND it with 1? Just to take byte number 0? Yeah, apparently. Oh, of course, because direction is either 1 or 0. So we generate a random number and we take whatever the first bit is. We store that. Otherwise, we take whatever is in the level data. We load the type start direction byte. We AND it with this so that we get only those. We do a logic shift to the right, so those 2 bits shift to the right. We compare that to 2, and then we set the Y direction. So what we did for X, we now do for Y. And we adjust the enemy counter, but that's not new. No, this is setting the Y direction and the X direction. Okay. Okay. So we've actually implemented those values that we saw in the beginning for the sprite direction, and that's it. That is the whole change. So the most of the code here is in the I would say in the zombie behavior, and of course in the mummy behavior as well. But the zombie behavior, because it has all the different aspects, so it's good to have a little bit of a look at that. I have to say that if you're watching these videos all in a row, you may not notice, but between steps 32 and 33, there was quite a large amount of time. And the good thing is that I didn't need a lot of time to get back into the code. It's pretty easy to read. So that's it. Thanks for watching, and I'll see you in the next one. Bye bye.